Welcome to this explainer. Today, we're zeroing in on a genuinely critical piece of power system protection, the RET615 relay, and specifically how it tackles overcurrents. Now, let's jump right in. The absolute core concept we've got to establish right out of the gate is that in any electrical network, not every overcurrent event deserves the same response speed. I mean, you definitely don't want your protective relays reacting to a routine heavy load the exact same way they'd react to a catastrophic system failure, right?
To put this into perspective, just imagine this scenario for a second. Should a protection system treat a temporary 2-second motor startup surge exactly the same way it treats a massive voltage short circuit? No way, of course not. If it did, you would literally be shutting down your plant every single time you turned on a machine. Or worse, you'd be burning down your switchgear because the relay just waited too long to trip during a real, actual emergency. And this right here is exactly why the RET615 relay uses a multi-stage overcurrent protection scheme.
So here's our quick roadmap for this explainer. First, the overcurrent dilemma, then 2 tiers of protection, the patient layer, the impatient layer, phase and ground application, and we'll wrap up with coordination and misfires.
Section 1. The overcurrent dilemma. Let's look at why setting thresholds can be so tricky. You might be wondering, why isn't a single threshold enough? Well, it really just comes down to the fundamental difference between two very distinct threats. On one side, you've got a sustained mild overload. This is moderately elevated current for a longer stretch of time, like a huge machine just working really hard. That requires patience from your relay. But on the other side, you have a massive short circuit. This is extreme current happening right now, which absolutely requires instant action. If you try to force a single timing rule onto both of these, you're going to fail. You'll either set it way too sensitive and cause all these nuisance trips during harmless surges, or you'll set it too slow, which leads to incredibly dangerous, damaging delays when a real fault actually hits.
Section 2. 2 tiers of protection. How we build a layered defense system. The way the RET615 relay tackles this dilemma is actually brilliant. It runs 2 entirely different protection philosophies side by side on both the high and low voltage sides of the transformer. Think of it exactly like a 2-tier home security system. Your first tier is a general motion-triggered alarm. When it senses movement, it gives you a short delay, maybe 30 seconds to punch in your code and disarm it before things escalate. It's patient. But your second tier? That's a glass break sensor. If that sensor goes off, there is 0 delay. It calls the police instantly, because glass breaking means someone is already inside. Your electrical network needs this exact same kind of layered defense.
Section 3. The patient layer, also known as PHLPTRC. Okay, let's translate the alphabet soup here. PHLPTOC stands for Phase Low Protection Time Overcurrent, and it implements standard ANSI 51 functionality. This is our patient layer, like that motion alarm. Its whole job is to provide time-delayed protection against sustained overloads. It essentially sits there and waits to see if an overload condition is actually going to stick around. And crucially, it's designed to coordinate with other protective devices further downstream before it ever decides to issue a trip command.
Notice how coordination curves typically swoop downward. With time on the vertical axis and current on the horizontal, that swooping curve basically means at lower overcurrents, the relay waits a lot longer before tripping. It's literally graphing patience. A standard PHLPTOC setting might allow, say, 2 to 10 seconds of tolerance at 150% of rated current. What that does is give a downstream breaker, which is much closer to the actual fault, the chance to trip first. That isolates the problem without you having to shut down the entire upstream network.
Section 4. The impatient layer, or PHHPTOC.
But what happens when being patient is actually a liability? That is where PHPTOC steps in, implementing ANSI 50 protection. This is our glass break sensor, and honestly, this layer has absolutely 0 chill. It is configured for instantaneous or very short delayed clearing of high current short circuits. It operates on a very simple assumption. If the current spikes to an extreme level, it cannot possibly be a normal operational surge. It must be a bolted fault, and it needs to be cleared from the system immediately to prevent catastrophic damage.
So how you configure this stage is absolutely crucial. Unlike the swooping, sloping curve of our patient layer, PHPHOTOC operates as a flat, incredibly fast cutoff.
The rule of thumb here is that its threshold has to be set above the maximum credible load or inrush current. That way, it ignores normal startup surges. But it has to be below the minimum expected internal fault current. When a severe fault crosses that specific line, this high stage might be set to trip in under 50 milliseconds. That's a massive difference in tolerance philosophy for the exact same relay running in parallel. Basically, whichever stage's criteria is met first, that's the one that issues the trip.
Section 5. Phase and ground application. So far, we've been talking a lot about phase overcurrent, monitoring those standard phase lines. That is your 50-51 protection. But the RET615 applies this exact same two-tiered logic to ground and neutral currents as well. That's designated as 50N or 51N. Ground faults don't always produce massive phase currents, especially if you're dealing with highly resistive networks. But they still absolutely require that same layered approach, a patient, time-delayed low stage for sustained mild ground leaks, and a fast, impatient high stage for severe earth faults.
Section 6. Coordination and misfires. This is where the rubber meets the road.
All right, let's do a quick interactive quiz. Imagine a really large motor starts up downstream of your transformer. It causes a brief current surge up to 300% of normal load for 2 seconds, and then it just settles back down to normal. Based on everything we've just covered, which stage should trip here? The patient low stage or the impatient high stage? Think about it for a second.
The answer? Neither. If your system is properly coordinated, neither of them is going to trip. This exact scenario is a stress test for your low-stage time delay settings. The patient stage has to be programmed to tolerate a 300% surge for that 2-second duration without throwing a nuisance trip. Meanwhile, your impatient high-stage threshold needs to be set well above that 300% surge level so it never even recognizes the event as something worth tripping over.
If you plot this out on a coordination graph, you'd see a specific point indicating that motor starting transient. In a perfectly coordinated system, that point sits safely below and to the left of your actual tripping curves. It's visual proof of perfect coordination. The motor starts up, the current spikes briefly, but the whole event stays safely out of the danger zones of both the patient and the impatient stages.
But what happens when we get this wrong? It's really easy to fall into the trap of thinking, hey, more sensitive settings are always better, right? Actually, no. Applying overly aggressive low-stage settings without proper time grading, or worse, relying only on high-stage protection, causes miscoordination, and this is a huge warning. Miscoordination means you might nuisance trip on harmless transient conditions, or you fail to isolate just the faulted section. So instead of just tripping a local breaker, you trip a main breaker further upstream, and you unnecessarily black out massive parts of a plant for what was just a tiny, localized problem.
And that leads us to our final thought today. The RET615 gives you all the tools, the low stage for patient, careful coordination, and the high stage for impatient, immediate action. But it's entirely up to the engineers configuring it to strike that perfect balance. So take a moment to think about your own facility. Are your high stage instantaneous settings set so low that they're accidentally bypassing the carefully planned network coordination of your patient low stages? It's definitely a question worth asking before the next real fault tests your system. Thanks for joining me for this explainer.